I am Bhavidhir V. Bharadwaj. Welcome to episode 23 of Genesis of Tomorrow. The following is a conversation about distributed quantum computing, models and frameworks, and much more with Miss María Gargera Garces, quantum informatics researcher at the University of Edinburgh, former quantum software developer at the Google Summer of Code, and co founder and project director of PQB Quantum Youth. Also, 86.1% of you watching this have not subscribed yet. So if you get even the slightest bit of value from the show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing you such wonderful guests over. And now, without any further ado, let's get right into it. Enjoy and thank you. And we are rolling now. First of all, welcome on the show.
Thank you. It's a pleasure.
And I think it'll be lovely if you start by giving a general background of your domain and what subject matter do you hold your expertise into.
Sure. So, for those who don't know me, I'm María Garcés. I've been working in the quantum world for the past few years. I have a background in physics. I did my bachelor's at the University of Bath, where I specialized in photonics and photonic hardware simulation. Alongside my studies, I've been working in the quantum industry. So, I started working in quantum networking research in Cisco, where I spent about 13 months in London. I was there when they were starting to build their initial quantum team. And since then, I did a lot of work in the quantum open source community through various projects that were either funded through industrial funding, either in startups or through academic funding with just fellowship programs. My last role was in IBM Quantum, where I was part of the EMEA community team. So I did a lot of science communication and quantum communication. I still participate in this world of talking about quantum through my social media. So I'm very active on LinkedIn. And I also am the director of a project called BKB Quantum Youth, which is led by students and for students with the objective of communicating quantum information and quantum knowledge to students who might be interested in pursuing a STEM career or who might be just looking at what things they may want to specialize in or think about before choosing the degree. So we're mostly focused on young students that might be in high school level learning. And also at the moment, from just a career perspective, I'm doing my PhD at the University of Edinburgh, where I'm working on distributed quantum computing, which is relatively new to me, but is a good bridge between my past work on quantum software implementations and quantum networking research. And yeah, that's pretty much me in a nutshell.
What piqued your interest towards the quantum domain?
So I started working on quantum networking. So that's telecommunications and how we might send quantum information from one point to the other, more from the theoretical or the software perspective, rather than like the actual physical photonic implementation. And at the moment, I am working on seeing how that level of the overarching architecture would interface with computation. So how we might distribute an existing computation in the context of perhaps having machines that have less qubits that we might need for an algorithm. So let's say we have a 1,000-qubit algorithm, and we have, I don't know, multiple 100-qubit machines, but not a 1,000-qubit machine. I work on seeing how we would partition a computation through those different machines.
Okay, so you have a very, how do I say, intense sort of journey that I can touch upon various aspects of, and I would love to do so in a singular fashion, starting from your work in educating young people, right? What do you think is the current status in regards to quantum education, and what work have you been doing in this field, and how do you think it will pan out in the next few years?
So I think education is an interesting question because when you educate people, you need to think of why or what are you educating them for. And there's various ways of thinking about the future of the quantum industry. There is the perspective that's shared by some people that you will not need, quantum specialist for every single aspect of the future quantum industry, the same way you don't need them in the current software industry, right? Not everybody that's a software developer has a PhD on software system architectures and knows exactly how everything works. They are just capable of taking a problem and resolving it with the existing tools. So I think for people who already have a background in computer science or who have a background in physics with a knowledge of how to use software, especially Python, there's a relatively available entry point with things like Qiskit or other programming tools that already exist and are available in industry. That being said, at a lower level, for students who might not necessarily have those skills yet, there's very little, close to nothing, that's available that's actually supported by people who know what they're doing. So that's vetted in some way or developed in a way that isn't just people talking about hype and using quantum as they would use the word AI and confusing the two of them, right? Because that's a massive problem that we have right now in the quantum world, especially when we talk with people who are in industries adjacent to it and not directly on it. So it kind of depends on where you're coming from, but regardless of wherever you were capable of getting to that initial entry point in which you might learn how to use a specific quantum software kit, there is a very big barrier when you get past the initial learning how to use it point, which is what can I use it for? Because the number of quantum algorithms that we have right now that are actually useful is really limited. And the applications in which we can actually use these algorithms in are still in active research. So there's this massive jump in between I know how to use these kits. I kind of understand the concepts and the ideas and the quantum mechanics behind it at a basic level, and I can do something with them. And this gap is what is currently trying to be joint both in academic institution and industrial bodies, but it does leave learners in this vacuum of, well, I can either specialize in this and go do a master's and go do a PhD and make this my entire career in my life, or I can just lose interest in it and stop looking at it because there's not enough open opportunities for somebody who doesn't understand the higher level or the more complicated, breach that we need to look into. So it's kind of an interesting world in which, at least to me, it feels like we're promoting and we're educating people, but we're not telling them this initial truth that right now the problem is in between the starting point and the advanced point, and what we need is to connect both so we can actually get software developers that do useful things. And that's what the focus and the strengths and the education should be geared towards, is actually showing open questions and showing the problems rather than just learning how to use certain kits that you will then not be able to implement in the next 5-10 years because they will not directly affect whatever industry or world you're working in, unless you want to, of course, completely move to the quantum world.
I think with the advent of so many different research areas in quantum technology and quantum science in general, it allows for people from different set of backgrounds and skills to be able to contribute to the existing research and its advancement in their own unique way.
Yes.
May they come from a background of biology, chemistry, pure sciences, or computer science, technology, engineers, they can contribute in their own significant way. When you're working with high schoolers, right, what sort of a temperament do you see in these young people in regards to their perceptiveness and their prior prerequisite knowledge that they already have with regards to the quantum world?
So the work I do with BKB Quantum Youth is first assuming that people know nothing. It's a complete blank state, and whatever thing that even if they know things, it's probably a metaphor or a way to, simplify a very difficult thing that we don't even understand, because quantum mechanics is just straight up wrong. We've demonstrated that in an experiment, right? So it's like a metaphor at top of a model that isn't even fully complete in the sense that it's not, a unified model. So we just try to create the rules of how we explain things. So we work in settings of series. So these are various videos of various pieces of content which are supposed to feed into each other and introduce the student or the person who's seeing this content to a concept in the quantum world in a linear way. So we'll start from a very simple initial question or initial setting of the things that we want to show them, and then just slowly progress through that. So, for example, I lead a series on the quantum industry, and the first question and the first thing I put out there was like, what is a quantum computer? What am I talking about when I'm talking about a quantum computer? And then I started introducing other concepts like, what is open source in the context of quantum? Why is it useful? Why is it important? Right? So kind of trying to have a linear story in which you've previously defined the concepts, and especially when we look at it from a more of a implementation perspective. So from a more of a software perspective, we have a series on quantum computing in which we've actually explained what single qubit gates might be, what different rotations of a qubit might mean. It's mostly about showing visualizations and showing direct results of how this might look like to the student, because going from the very beginning to the very end of an algorithm, which is something that you see quite a lot in conferences, is really shocking, especially to somebody who might not have any background whatsoever, even in classical algorithms. So we just try to take a very, minimized approach of defining everything really well and making sure that we're not misleading students. We actually vet every single video that we do between the different people working in the team, which is a group of people working now in the quantum industry, in quantum academic settings at bachelor's, master's, and PhD levels. So for us, it's all about making sure we say as little as possible, but that we send those messages across in an interesting way that's very visual, that is focused based on examples, and that might lead the student to ask themselves further questions. So we don't just say, this is fact, but we say, this is how we, showcase this concept. This is how we think about this concept. This is how people visualize this concept. And this is how this concept may lead to the following questions or to the following thoughts.
On a more, as an anecdote for people who have turned in, if I'm a person, a complete novice who's entering towards learning about quantum stuff, any facet of it, what are the most common pitfalls that I can find myself fallen into?
I think believing in magic is probably the biggest issue in the quantum industry, right? And this is something I think is a symptom that is not particular to the quantum industry, but it's interestingly persisting in the quantum industry because there is this variety of people working in this world who have completely different languages, right? And I get this a lot at work where there's a mathematician, there's a computer scientist, there's a physicist in a room, and we all may be using the same words but don't mean the same things, and we all visualize the same behavior, the same problem in completely different ways and in completely different languages, right? And that means that when information is spread, it's spread in non-coherent and non-consistent languages, and people pick up from it what they want to hear, which is understandable, but a very difficult, mistake to undo, especially when it starts sinking and it starts becoming this big thing. So the best example for this is the latest Google announcement where in the news, in BBC, they were talking about this incredible advantage in which the chip could solve problems so much faster than any supercomputer, and it was amazing. And there's even been, late night show skits on this, and people keep talking about it as the most amazing thing. But in reality, the problem they were solving was a purely quantum problem that only exists in the context of quantum computation. And it's incredibly cool and interesting for that people working on this problem, people studying the complexity and the cost of this specific problem. It is something that's advanced, but it doesn't really affect anybody in the sense that it doesn't prove that this chip can do more things than a current supercomputer. Sorry, I keep saying supercomputer because it can't, because quantum computers are still work in progress, and they're going to continue to be work in progress for the next few years. So it's about giving the right context to people is very difficult and very often not done. And even if it is given, it's not taken by, the people who then retransmit that information, which leads to a lot of confusion, which in the long run, at least in my opinion, will create a sense of dislike or misunderstanding to what quantum promised and what it actually gives to society and to industry. And that's why there's this conversation about the potential quantum winter in the future, and why we think that all the investment in this industry might fall down at some point or at various points through its progress, because there will be a point in which people will ask, okay, show us what the benefit was. And people in the quantum world will have to say, well, we never promised this because this is not what we were saying at the time. You just misunderstood us. So, yeah, I think that's quite a difficult problem, not just in education, but just generally in communication of information, especially in an industry where there's so many people coming from very different worlds, talking together about a same world that nobody understands.
I think that what you touched upon right now is something sort of a trend that even currently exists. For example, people who are pursuing a specific research in quantum computing, and they are able to somehow gather funding for that particular project, somewhere down the line they might have to curtail or take a step back from their original goal just to be able to show some sort of a tangible outcome or result to be able to continue that research and getting that funding. Do you think this is a very I don't know, current present challenge in the area of research and academia related to quantum computing?
Right. I mean, yeah, I mean, that is, I suppose that is something that happens, but that is just kind of a symptom of what the academic world is, in the sense that you get funding to, to investigate something that's a current problem or current issue in the world generally, or in the world of quantum. And if you want to renew this funding, you need to show something for it. You need to show that there's been some advancement, or that there's some purpose for this to continue doing. So I think that is a healthy thing, in the sense that, like, it is good that we're not just, throwing money into holes. I think it's more of an issue, though, when there's over promises or over showcases of things that don't exist. And I feel like, obviously, this is very generalized. You would have to go case by case. That is more of an issue within the quantum industry than within necessarily quantum academia. Simply because industry, well, it's competitive, and you need to have IPAs, and you need to actually showcase something that your company's doing, right? And there's all these quantum startups who are all doing very similar things, and sometimes the purpose of the startup isn't clear. Obviously, this is not the case for everything, but there is a lot of people working on these problems in industry who might not have the background to work on these problems in industry in the measure in which they're working on them. So it is an interesting, discussion of how much funding and where is it going in industry, and what are people doing with the funding, and how are they getting this funding, what are they promising, and what can they actually perform compared to what they're promising.
Somebody who's wanting to begin a venture in the quantum field, what do you think are the most prominent areas which will be able to reap short-term benefits? I mean, long-term, sure, but be able to yield some short-term results in the short term.
Right. Well, I mean, just coming from that same Google announcement, error correction right now is a very cool place to be. I mean, we just proved experimentally that, like, the existing theory is true and is working. So that's definitely, especially if you're coming from like a pure maths background, it's a very interesting thing to explore. I am personally less of a error correction interest person. I think, at least for me, something like algorithms would be an interesting thing to pursue for people, mostly because there's very few quantum algorithms that actually show, a exponential or even any type of benefit in terms of the time complexity that they're running through compared to their classical equivalents. So just trying to find problems and ways to solve problems in which quantum computers actually show benefits. It's a very interesting area to work in, and it's not an area that necessarily requires as much background as other aspects of quantum. And then, of course, I will always be pro research in quantum networks, simply because there is a very, very interesting world of communicating and of connecting things with each other, and quantum networks reduce theoretically the cost of sending certain messages. And not only that, they present this massive security benefit that is the reason why there's so much investment in things like the quantum internet or quantum networks in general, especially from bodies like banks or government bodies who want to make sure their data is secure from future quantum computers. So I feel like those will probably be the three hottest areas for people to work in right now. Is just quantum communications, quantum algorithms, and error correction. And depending on what your background is, you might see yourself fitting more into one of these or the other. But those would be my top three at least.
Okay, maybe exploring this tangent a bit more. First of all, uh, before we move on further, what is quantum informatics, right? How does it fit into the overall puzzle of quantum computing and its relative stature in comparison to the classical counterparts and classical information and all that? And again, examples
Right.
and implications of it.
Right. So when you're talking about quantum informatics, you could be seeing it from two perspectives. So you could just be saying, okay, we're talking about the quantum world of computer science, or you could be saying we're talking about quantum information theory. So in the world of quantum information theory, right, what we're working on is a different starting point, a different unit of information. We're not working with a classic unit of information, which would be this binary zeros and ones, but with an actual quantum body that might be in different superpositions of states, meaning that it might live in both or in a 0 and 1 state up until the point in which it's measured. And it is this idea of Schrodinger's cat that might be dead or alive until you open the box, right? And also, not only that, but quantum information has some fun manipulations or some fun interactions that it can do with other quantum information due to the laws of quantum mechanics. So we can do things like teleportation, which we cannot really do with classical information, just because classical information is much more straightforward. It's an artificial thing that we've created in order to be able to compute things, whereas quantum information, in a sense, is a abstraction of a real object that occurs in nature. So we kind of get certain powers or certain rules that we can play around with that don't really exist in classical information. And that's what leads to all this interesting discussion about higher security or things that might protect more or things that might cost less in terms of time or resources using quantum information, which then leads to the creation of quantum computers or quantum networks, right? So it's basically quantum information science is the basic observation of all of this at the lowest level of, okay, I have these qubits that may represent superposed states, and I can manipulate them and then measure them and explore a larger search space or a larger computational space than I would have been able to do in the same time and in the same space with bits. But how we get this advantage and this actual result of getting something better and something that's, more useful at the end of a computation is very difficult. The study of how to get to this point, to get to this benchmark of, okay, I have quantum advantage is incredibly complicated. So that's where the different on the study of both types of informations comes in, and that's when all these stats and all these experiments come in exploring what exactly are we interested in and why. And we don't have an understanding of that, because just by defining, the fundamental things that may lead to advantages in the classical world, which would be, for example, parallelism, so being able to run different parts of an algorithm on different machines at the same time, and therefore leading to like a higher speed up and less time overall to run an algorithm. That doesn't really apply in quantum computers, because in quantum computers we don't, the concepts of like sequential runs and parallel runs don't translate to the same things, and this all comes into the world of, or into the in language of information, and what is information, how does information vary, and how does it interact with each other, if that makes sense.
It does. It does. Uh, Again, taking a step forward, what is the distributed approach of quantum computing? And in particular, I think it is one of the most viable approaches towards creating a quantum internet, if I'm not wrong,
Yes.
and quantum communication, of course. What it is, firstly, and then secondly, what are the challenges to be able to fulfill its absolute potential? May it be communication protocols or error mitigation, but yeah.
Yes. So I think what it is probably its number one challenge, right? So distribution is something that occurs in the classical world, and also has already occurred in the quantum world, because one of IBM's computers, its system 2 it was 3 chips that were connected between each other. So like the distribution and the use of various chips in order to create a computer or a system that has the more power or more access to power than if it was composed of one chip, has already happened in both worlds. But the reasons for which it may happen, or the benefits that it yields, are slightly different, in the sense that in the classical world, we have a much better understanding and control over information, and we have an understanding of how we can manipulate systems and how we can make them collaborate between each other in order to reach ideal scenarios in which we're actually achieving results from our like massive computations that may be required when we're simulating, I don't know, many-body physics or any other, big computational, well, AI probably is the best example of this, right? But in the quantum world, we don't really, the purpose of parallelization isn't really understood, in the sense that parallelism may not mean, at least in the sense of it yielding an advantage or yielding a speed up, may not mean the same things, and it's something that is currently being explored, but we don't really know exactly how parallelism may come into play as a resource in the quantum world, in the sense that one of the initial theories of why quantum computers may yield advantage over classical computers was entanglement. This idea that like, oh, the entanglement's the whole point, and entanglement's the reason why we get speed ups. But that's actually been proven that that's not true. Eating up more entanglement, that an algorithm eats up more entanglement, doesn't directly lead to it being a better algorithm, or an algorithm that presents a speed up compared to its best classical equivalent. So this purpose of parallelism is a question, which leads to the other purpose, for which you might want to have distributed systems, which is you simply cannot create a chip that's big enough or that will fit in a reasonable space that has the required resources that you need in order to run your computation. And that is kind of the context in which it is being used in at the moment. So at the moment, a lot of distributed quantum research is focusing on just being able to map a computation. So usually that comes in the form of a circuit in the current literature, to multiple partitions, so multiple machines that may be able to together give you the result of the circuit, but they wouldn't be able to do it separately because they wouldn't have enough resources separately. This can be done with the layer of classical networks, which is what currently occurs in most systems that exist. So most quantum chips that are currently connected are connected with classical networks, and that becomes a really interesting question, because it requires probabilities, because you can't, when you send something through a classical network, you need to actually collapse it and you need to get one result. So you kind of close your search, like your mathematical search area of quantum, and you redefine it in classical. And then you send that information over, and then you do your next computation with maybe the information you got here, or maybe you were doing multiple one of these computations together, you got all the informations here. But this sending through a classical network requires you to do it multiple times and get some sort of like quasi-probabilistic distribution, and then kind of we then call the recomposition of all these results circuit netting. So that's kind of what occurs right now in the industry. If you look at existing computers that are currently available that you can access, if you play around with Qiskit, if you play around with PennyLane, that's what's happened. You're doing circuit cutting. But there's also the alternative to this, which is circuit distribution, which assumes a quantum networking layer, in which you don't have to worry about doing all these shots because you're not collapsing or you're not cutting off the computation in the same way, because you actually are kind of continuing the computation through a quantum link. And there, what you're trying to do is just getting the most ideal partition for your computation that is fair for all the different machines that you're sending it on. But we're still kind of exploring the benefits that, getting this type of distribution may yield in the long term, because that's still an open question. And it's incredibly interesting because, there's no equivalence to like Amdahl's law, Brent's theorem. All these things don't really exist in the quantum world because our concept of parallelism isn't translatable.
Okay, taking a speculative thought trail, how long do you think before a quantum internet of sorts is established? And before that, in what ways would it be particularly utilized? Because current classical internet seems to be solving pretty much the need of people. So why is it needed in the first place, and what specific use cases will it be able to be more prove to be more viable?
Right. So just as a disclosure, I'm not a quantum internet specialist. So I mostly look at quantum networks right now, at least from the perspective of connecting computation. And the reality is that quantum computers will probably be an offloading processor unit, at least from my perspective. There'll be an offloading processor unit in supercomputers. I keep saying superconductors, I don't know why. Supercomputers, right? There'll be something that hopefully we get an understanding of what BQP is and maybe how it differs, or how certain problems may require some sort of quantum advantage. We might be able to send certain parts of a computation to a quantum processing unit and therefore just worry about the advantage there. Or they might be used just to run, the initial original purpose, which is, physics simulations and advance our understanding of the world around us in the quantum plane. But if we want to think of quantum networks as something above that, so something above this context of quantum computing and something separate to that, I think the number one, purpose for them, or the number one, runner-up of why we should consider this is security. So there is this danger or this worry that quantum computers and our manipulation and understanding of quantum computers will get to the point in which we will be able to, break encryption, break RSA. I think it's called Q-Day, the day in which quantum computers will actually be able to get to the point in which we're breaking all the security that currently, safeguards us all from bankruptcy and identity theft, because at the end of the day, everybody has so much information in different devices that is being protected by different security measures. And if we have a computer or any device that can break these security measures, a lot of the way in which our world runs becomes unsecure and therefore very, very problematic at different layers. And quantum networks could possibly prevent these breaches from occurring. Now, the ways in which these breaches occur and the ways in which quantum networks could be implemented in a way in which they protect our current, networking systems in general from these attacks is still, again, something that we need to research and something that we need to keep developing. For a start, no quantum network can send information with a classical network. So it's not a question of, destroying classical networks as they exist and replacing them with quantum networks. That for a start doesn't work because there's, physical principles that don't allow us to send information, at least in the teleportation protocol, right, through a quantum network. But it would be an interesting add to existing networking systems. And it's something that industry is looking at, something that Cisco is looking at, something that Jupyter Networks are looking at. Is this, how would an addition to our existing networks benefit, or how could we implement it in a way in which it gives us additional protection and security against these future machines which come from the same initial information, from the same basic technology? And that's a very interesting question. Unfortunately, we don't, or at least I don't have a full answer for it. But as I said before, at least for me, it's top 3 hot areas of research at the moment. And it's, especially if you come from a physics background and a photonics background, is a very, very cool thing to be looking at.
On a personal level, what do you think is the most interesting thing that you are currently working on?
Oh, that's a great question. At the moment, I am really interested in this idea of parallelism and how it might affect speedups. It's of course a very big, vague question that needs to be, defined in the sense that there needs to be, a mathematical representation of the problem, right? And at least to my understanding, there isn't really in the way in which I'm looking for it, which is a resource that would allow us to that we would be able to exploit by distributing computation through various processors or various units, and that would lead us to a speed up compared to classical devices. So that would be kind of what the resource gives us if we use it, if we consume it. But of course, that is a very big question. In a more, let's say, reachable note, I think another area that's interesting is I'm currently exploring different quantum computing models. So most things that are available right now when you search up quantum computing is the circuit model, which is just like the implementation of unitaries through gates. And these gates are physical things that exist within machines, or at least in one form or the other, but not all qubits, because qubits are, as I said before, they're actual, in a sense, they're abstractions, but they're abstraction over an actual physical object. So not all of these physical objects interact with gates and with circuits in the way that we understand it. So photons are like the perfect example of this. Photons don't really run with the circuit model. They run with measurement-based quantum computing and with fusion gates. But there's also other ways of thinking of quantum computation. There's quantum walks. There's the adiabatic and topological quantum computing. And I am currently trying to wrap my head around what and all these, to be fair, all these different models they're all universal in the sense that you can always translate a computation between them, but the way you translate a computation between them is not optimized in the sense that I can't just get Schro's algorithm. I can't create a circuit for Schro's algorithm, translate it to its measurement-based equivalent, and think that this measurement-based implementation of Schro's algorithm is the best implementation of Schro's algorithm that I could do on this different computational model. So what I'm trying to do at the moment, or I'm trying to look at the moment, is how these models differ from each other and what are the interesting, let's say, dynamics or behaviors that we can look at that might give us an insight to quantum advantage and to quantum distribution through these different models.
What sort of an insight have you been able to gather or garner up until now?
That's a
In this
great
particular
question.
area?
When I discover something, I'll be sure to publish it. But at the moment, I'm just wrapping my head around the models because that, believe me, is complicated enough.
I mean, okay, maybe tweaking the question and approaching it from a different angle. How do you think studying all these different and novel ideas and concepts impacts you and affects you at a personal level and changes your approach towards understanding reality in general?
Right. Well, I think first of all, it's just fun. It's interesting to learn all these things, and it's interesting to explore our understanding of quantum computing and quantum distribution just from a purely academic interest perspective, right? At least for me, it's always very humbling and always very interesting to see that most of the things that um, we currently understand of these computers and we currently can manipulate of these computers are probably wrong, in the sense that they're not optimized, they're not the best possible solution. And even if they are the best possible solution, we can't really always prove why they're the best possible solution. So, I mean, at least right now, I'm working in the academic world, so I'm working research, and it wouldn't be research if we knew what we were doing, despite of what some people might want to lead you to believe. So, at least for me, it's just about hopefully contributing to this, knowledge that we have as humans of how these machines could benefit us in the long term. And it doesn't really go much deeper than that. I mean, I don't pretend to have a real understanding of how any of this works, because I don't really think anybody does. And anything that's published, hopefully, does have some setting or some measures in which the result that was achieved is defined. At least in the world of theory, we work in constrained models and in constrained theories that have underlying assumptions. And that's not how the real world works. And that's why experimenters are so incredibly important, because they're the ones that actually, showcase how reality really works and how some models may be faulty, or how some models might be incredibly good at modeling certain things that we weren't expecting they would be good at modeling, right? So it's just about for me, it's just about being part of this process, of this contribution. I really, it's, especially physicists love talking about like all the consequences and all the direct, the multi-world theories and all these different things. And at least for me, I feel like I'm still at a low enough point in my personal vision of how things work that I wouldn't have the confidence to, align myself with a specific view of the philosophical consequences that these systems might have. But it is certainly an interesting discussion to at least be aware of. Now, when it becomes part of industrial claims, that becomes an interesting scenario of like, what are we talking about now? Are we talking about, the physical results that we're actually achieving, or are we talking about how we may decide to interpret them? Yeah.
Would you say that is exactly why the work that you do with BQB, Quantum Youth, and at educating people in general, uh, particularly this is why it holds so much importance to you? Because
Yeah,
like by doing that you are also some way being able to explore these different uncharted territories that you might want to pursue in a more thorough manner or from a different lens.
yeah. I mean, for me at least, sharing what you know and opening the door for the people after you is almost, a duty, in the sense that it would be incredibly unfair that you've been able to have all these opportunities because of the chances of life and the situation that you've been in. Because at the end of the day, everything's a roll of dice, right? And for you to not enable the people after you to get into these positions and to learn these things. And at least the way I met the quantum world was relatively coincidental, in the sense that there's a lot of people with which I work at the moment that tell me, oh, I learned that quantum computers were developed when I was 16, and I kind of geared my entire career towards this. And that's not really how it happened for me. But that, I feel like that might also be because that information, quantum computers existed, and this was an industry that was maybe interesting, or a academic area of research that might have been of interest to me, wasn't even available at the time, at least in the context in which I was learning. So, opening the door and just showing as many people as possible that this is really cool area of work that they might not be aware of, that does have, technically speaking, quite a lot of funding being thrown into it at the moment, is something that I think is good. and being able to create this platform that hopefully, at least I always hope, doesn't feed hype, but rather shares, even if in a small way, small, interesting, real knowledge that in a format that students may understand and might get excited about, is important. So for me, it's less about exploring new things, but rather about showing people real things that we have a certain understanding of right now, and being like, look, this is something that's really cool that you might be interested in as somebody who's currently searching for their path and the things that they might want to explore during their industrial or during their academic career, whatever they want to be doing. I recommend you at least check this out. And in the checking this out and showing them what it is, being straightforward and honest on a real abstraction or in a real understanding of our model, and not just saying these computers, they can do everything and so much more, they're the best thing and the biggest thing ever, and they're so complicated that we can't really explain them at all, because that's not true. We can explain our understanding of quantum computers really well. What we can't say for certain is that the way we understand them is true. But that change in language and that change in purpose, at least, is important for me. And I feel like contributing to this creation of opening doors and of showcasing and opening windows for people that are done in a purposeful manner is, at least for me, really important. It's something that I'm particularly passionate about, just because I think it's a good way of using my time.
You also were a quantum software developer at the Google Summer of Code
Yeah.
in 2022, if I'm
Yes.
not wrong. So it would be fine to say that you have got this experience in the industry side of things, where software developers are working and all that jazz. How do you think the current diaspora of quantum software developers, individuals who are working towards doing that, first of all, what they do, secondly, the people that do stuff, what challenges do they face, and what are their pain points of sorts? What were your pain points when you were working in that area? What was your overall experience? And last but not least, what is the way forward for quantum software arena?
So I think, this Google Summer of Code program is something that Google runs every summer, and it's basically some sort of fellowship of grant for development of open source codes. And at least for me, I think open source is such an incredible way not only to contribute to existing software packages and of learning through this contribution, but of also of building, and developing future quantum software developers, and understanding how the community works, what type of projects might be interesting, what type of projects are being developed by who, is such an incredible way, especially for people who already know how to code, to get to that point. So just this is a little advert. If anybody's already has some experience in coding, maybe a background in computer science, is interested in getting to the quantum world, quantum open source is like the way to go. There's so many ways of doing it. The Unitary Fund has so many different projects available. They run this yearly hackathon called the Unitary Hack, in which you can actually program in these projects for bounties, which is I participate in a couple of times, which is really cool. But I think it's talking about quantum software developers is a difficult question, because the first response to that question is quantum software developers where, for what's the purpose? Some people who are quantum software developers are building quantum kits like Qiskit, or in the world of quantum networks like NetSquid or Sequence. Then there's the quantum software developers who are building platforms. So people at Classic, that might be, for example, building the platforms in which you then code in the kits that exist and with which you actually connect to hardware devices perhaps. And then there is the people building algorithms, and all these different purposes and all these different roles that quantum software developers have now and will have in the future are really different, and at least from my perspective, are filled by very different people. So it's a very difficult generalized question to answer, because the only answer I can give is I really don't know. I know how it might be useful and purposeful to develop connections between projects that exist, at least in the open source world, and how people might want to get to that point and start contributing to these points. But the how as a role they exist in the current quantum industry, at least to me, is still uncharted waters, and will probably be for a few years, because it's research. It's something that we're still developing. We don't know what we're doing, and it's fine. That's the fun of it.
uh, Artificial intelligence is being, at least attempts are being made towards incorporating both these technologies, quantum technology and artificial intelligence, to whatever extent possible. And recently, DeepMind created a sort of AI based quantum decoder to be able to mitigate quantum errors. And my question, primarily, what I really want to ask you is, to what extent do you think developments and advancements in artificial intelligence will be able to impact the progress that we are making with quantum technology in general?
I think well-developed and purposeful AI and well-developed and purposeful, quantum computing will hopefully work hand in hand and benefit each other. I mean, for me, AI is an interesting thing, because a few years ago we weren't calling everything AI, and things that in the past weren't being called AI are called AI now. I mean, the chatbots of banks have been around way before they were called chatbots. But I mean, for example, an interesting way of thinking about it is and chips, the way you actually develop or implement a computation through a chip, that is pretty much optimized through AI. And in quantum computers, just because of the complexity or the difficulty of like mapping computation to qubits, the way that information computation is routed to the qubits on the actual hardware will probably be done through some sort of AI. And especially in error correction, as the algorithms grow and as our power of computation grows, the way we decode errors, I don't see any reason why it wouldn't be done with AI, with some sort of deep learning system, deep reinforcement learning, system that will be able to recognize certain patterns of errors and correct them through computation. So I definitely think AI has the power to help us develop these computers and help us create models in which we understand the problems with these computers better. I also think that in terms of applications, hopefully, at least from my perspective, quantum and AI will be able to advance certain areas of research together. So, for example, in chemistry and in modeling chemistry problems, especially with the purpose of creating drugs and creating medication, AI and quantum might be able to help advance modeling and simulations of of drugs before they go into their initial trial levels from very different perspectives. So there is this idea of data-driven and model-driven development of drugs, and AI and quantum might be able to both take on one of these areas or sub parts of these areas and advance them further that we currently than how we currently work with these models, right? So I definitely don't. I don't have a background in AI, so I definitely am not qualified to talk about AI. But I don't see it as a problem. The only issue I personally have with AI, and it's not a problem with AI, it's a problem with just general science communication, is that both areas suffer with so much hype. And as people working in these areas, it is our duty to remind people of reality, of what problems really exist and what promises we've really made, and not of what news outlets might be talking about generally.
I completely agree to that. I still remember around 2-3 years ago, pre-COVID arena, time AI wasn't this hyped,
No.
trendy buzzword that it is right now. And I feel right now quantum is sort of going through or suffering the same fate of being thrown around as a buzzword without people realizing what those terms actually mean.
Yeah, I feel, at least for me, the symptom of how bad it gets is when things start getting joined. So, AI and crypto are very commonly joined, but then AI and quantum, okay, I sometimes understand it's not always used in the same, in the good context when they mix them together. But when I see quantum AI and crypto, I'm like, oh, okay, that would, this is,
Right.
by crypto, I don't mean cryptography. I mean like
Yeah.
crypto coins, right? When we get to those levels, especially, ice titles in an article, I'm like, oh my God, this is way too much. I mean, quantum and AI together is usually a bad sign, because most of the times it's not talked about in the context in which I was talking about it. It was just talked in the context of, these are the things that are going to change the world. But yeah, it's definitely, it's an interesting and dangerous symptom that we need to try to mitigate and control. The same way we correct errors in the computers, we need to try to correct errors in the news.
Also, umpteen times the people who are talking about this synthesis or amalgamation of quantum and AI, they themselves aren't most of the time individuals who are thorough in either of the subjects, or thorough in this area of synergy of both these subject matters.
Yeah.
And I think that is a common challenge that any industry or area of science and technology faces, where the scientific communicators umpteen times they themselves aren't coming from a background of thorough research or development in the field that they're talking about.
Yes.
And
No,
it
absolutely.
intensifies with the advent of chat gpt, right?
Yeah.
Artificial intelligence, these llm models. You just got to type in a prompt, and then you have this content that you can publish out into the world and garner followers and all those traction.
Yeah, I mean, good prepared science communicators are so incredibly important today and in the future that's coming. It's so, because obviously you can't always expect researchers to have the ability of communicate their research to a general public, because that's not part of the job, right? People can't do everything. There's certain skills that some people do have, and there's certain skills that people do not have. And it is very rare to have somebody who's incredibly accomplished in their scientific research, and on top of that can communicate it wonderfully to the population without without giving their personal opinions in the way. That's like, getting those three things in balance is really difficult, and I don't think we should expect researchers to get to that point. But having the people who actually specialize in communication of science make sure that their communication is correct, that it's purposeful, that they are capable of saying, these words of, we don't currently understand this, but this is kind of the understanding that we have of it, and this is how we interpret things, is so incredibly important. And especially in quantum, when you're mixing mathematicians, physicists, computer scientists, engineers, it is so, so crucial to have good science communicators that can translate reality and real results in a way that people understand and are still excited about them, but without creating the expectation that these machines work now, or that we know exactly how they will be used, is so important. So I completely agree with you there. It's I feel like science communication is so crucial to the way in which the quantum industry will be advancing, and quantum, investment will be advancing in the coming years. And it is very important too that, like, scientific communicators are specialized. Somebody who's talking about quantum is probably not capable of also talking about AI. I mean, maybe one individual who has an incredible background, maybe, but for the average communicator, they're not going to know everything. It's about making them people who are specialized in understanding of a field and able to talk with people about it.
Talking about science communication in general a little bit more, and I think I must pose this question to you as you're a researcher and also science communicator. If you are to characterize yourself, are you a researcher first before a communicator, or does being a communicator comes before being a researcher? And how does that tandem work?
So
Like,
I
how does it work?
think for two reasons. The first one is because I've been doing communication for much longer than I've been doing research, at least in the academic setting. I think I align myself more as a communicator. And also for the purpose that my current project is being done at the intersection of the Laboratory of Fundamental Information Science and the Institute of Computing System Architectures. I'm between two bodies. One that specializes perhaps more on the information and on the basics of a computer science, and the other one that's focused more on systems and in a more engineering perspective or a more networking perspective of applications. And because my project and my work serves as a bridge between these two bodies, I see myself almost sometimes, well, not sometimes, but hopefully in the future, as I develop through this PhD, I'm hoping to see myself as a communicator between these two languages, between, classical people who are working on distributed architecture and distributed systems and parallel algorithms, and quantum information scientists who are looking at things from the perspective of just quantum computing and quantum languages, right? I'm hoping, as my research develops and as I learned through this program, to become a translator in between research worlds, which in my world is still science communication. It might be internal science communication, but it's still science communication. And bridging the gap, even if it's between these two communities, in some way would, for me, be an incredible purpose for a career, right? Just being able to join the language between people and be able to translate certain, results to one group or to the other that might benefit further advancement would, for me, be incredible. So I identify as a communicator, even if it's within the context of research.
What would be your advice for the younger people just passing out from their high school, just into college, people who are just even people who are just for the first time have started to familiarize themselves with the happenings of the quantum world and quantum technology?
I think the main thing is to follow one's interest and to follow one's, purpose. Through my degree, I've done such a varied, I've explored such a varied area of work. I've done multiple things. I've done open source. I've done industry in big tech companies and in startups. I've worked with academic groups in physics and in maths. I feel like not committing yourself to something too early is very important, because there's so many different things that you could be contributing to. And if you're really early on, it's just about having your ears and your eyes open and trying to learn as much as possible, but also just accepting that sometimes you're just not interested in something and not feeling guilt for that, in the sense that there are so many people in the world of tech and science who want to advance our understanding of everything. And people specialize in things because they're interested in them, right? So exploring quantum is super cool, especially if you've got a physics background or a computer science background. But don't feel committed to, stay or advance the field if you're not interested in. Just make sure you learn as much as you can, especially as you arrive at university and you get exposed to all these new things. And if it so happens that you want to develop your career and your interests through the quantum pathway, just look for that. Look for those opportunities that will allow you to do that. There's so many things online. There's hackathons happening constantly. There's so many student groups that are open to new contributions. There's so many people creating videos and content and articles. Starting to read papers as you advance in your degree would be an incredible way to starting to see the research approach of how these things are being advanced and how they develop. Don't start maybe with like 2024 papers. Maybe something that's a bit earlier on is a good way to start, because when I started working in research, I was exposed directly to the newest things, and it was really confusing because I didn't have the previous background, and I kind of did this inverse learning process, which I don't think is the best way to do it. Maybe just like checking out the original teleportation paper, which is also pretty easy to read considering compared to other papers, and just how the basics of it all may work is a very good way of just, first of all, testing out if this is something that you want to pursue as a master's, as a PhD, or in industry, and second of all, making sure you understand and you create your vision of how these things work, and don't just follow the article that somebody wrote who might not have a background in this world about how these things work and how they benefit other people.
Okay, I also think I have to ask you this. Having worked in so many different situations and with so many different approaches to a particular subject domain, how do you balance between this sweet intersection that you have found between all these different aspects of quantum technology. And also, how do you balance between the workload and the workflow as a communicator, as a researcher, and the in general process of innovation, research, and creativity, maybe?
So I think, at least for me, I see my career as knowledge stacking. I'm just trying to learn. Honestly, I always feel like I don't know anything, and I'm just confused, and I'm trying to learn more and more and more. And at least for me, that's something that works, right? I feel like I have worked in many areas of quantum that have given me quick snapshots at a time of how that area of the industry was looking like, or how that area of research was looking like. And slowly, as I've been arriving to the stage in which I am in my PhD, I am starting to see how all these areas of quantum actually interact and actually may come together within a system, right? But it's still a process, and it's still something that I'm learning through. And I don't think even I'm the only one just by being a student. I even think that researchers that are specialists in this area of work are discovering these things themselves, right? So it's all about the journey, really. And the way to, being able to do all the things at once is pretty easy. It's just you're not able to do everything at once. Sometimes you end up doing less of one thing. Sometimes you spend months without doing one of these things that you're trying to juggle. Sometimes you're tired and you just do nothing and you want vacation, right? We're coming up with the holidays. I'm just going home. But I think it's useful to, as I've said before, just be purposeful and know how you want to contribute. What are you interested in? What do you want to advance? And kind of always move towards that and try to have a very clear idea of the things that you want to bring to the table and the things that you want to gain from the table, right? So for me, it's about making sure that people have access to an understanding to this world and have access to joining it if they want to, but also for me, the gain is the learning, and all the things that I'm exploring, all the things that I am being exposed to are incredible. Being able to talk with experts in so many different areas of physics and computer science and being able to understand what they're doing and trying to bring it together is such an incredible place to be. So it's all about juggling and trying to make things work. I mean, things like time boxing and a caffeine addiction help, but they're certainly not things I would recommend. So it's honestly, it's just about finding your journey, what you want to get from the table or what you want to bring to the table, and how those things may evolve as you know, or more or less through your journey through a specific area of research.
This final segment in the show that we do in all our episodes, what would be your word to humanity at large?
Oof, that's an incredible question. Feel do good. Do good is maybe simple, but very straightforward. I don't, we get so confused, and so we in this inner world, and especially, in politics and things like that, everything becomes kind of a fight and a versus, and I don't think that's the point. The point is just try to advance things together and make sure we're all moving together and all doing better for ourselves and for each other. So just trying to be purposeful and doing things that will benefit other people within the measures that you can, and within the measures that will also bring you good and, happiness is the most important thing. So yeah, very simple. Just do good.
Miss Maria Gragera Garces. I tried pronouncing the name.
That
Trust
was
me,
pretty good.
this was the best that I could get.
Yeah, it was pretty
Okay,
good.
so thank you so very much for being on the show. I personally love the conversation, and I'm sure that people who'll be turning in will be able to derive any and every kind of value that
Hopefully.
they'd like
Let's
to
go.
take from the show. Yeah.
Perfect.
So thank you so very much.
It was my pleasure. It was lovely to chat with you, and hopefully you have a great rest of your day.
Likewise. Okay.